Hi and Assalamualaikum. We are going to present investigation on high temperature low HTLS conductors. First, let's see the overview of the problem. Number one, rapid electricity demand growth. Economic growth and industry have led to an exponential rise in electricity demand, especially in our country Malaysia. So you can analyze the graph from case studies report from 1978 until 2014. The electricity demand growth is increased for industry, transport, agriculture, and commercial. As we know, electricity consumption in Malaysia is growing by around 6% annually, and this problem is straining the existing transmission and distribution infrastructure. Number two, overloading of transmission and distribution system. Expanding the transmission network have overloaded Malaysia's existing system, so the current infrastructure is struggling to manage the increased power flow to ensure that our reliability, stability, and concern about potential failures. Number three, limitation of right of way (ROW). As we know, our country Malaysia has a limited land availability and the difficulty of getting the required approvals and permission. So it is our challenge to build a new transmission lines.
Okay, next I will present to you about three different type of HTLS conductor available in our industry and how they are different with the ACSR conductor in terms of thermal limit, material construction, properties and costing. So for the first HTLS conductor, we choose ACCC, that is stand for aluminium conductor composite core that can operate at temperature up to 200 degrees Celsius. Number two, aluminium conductor composite reinforced, ACCR, that can operate up to 210 degrees Celsius. And lastly, we choose ACSS, that stand for aluminium conductor steel supported, that can operate continuously at temperature up to 250 degrees. And ACSR conductor, typically the temperature will go up to 75 to 90 degrees Celsius. So here is the ranking for each of the HTLS conductor compared to ACSR. So the first is ACSS, that is 250 degrees Celsius. Next is ACCR, and number third is ACCC, and lastly for ACSR. So from this we know that ACSR has lower thermal limit other than any different type of HTLS conductor. Okay, next we will move to the material construction and properties. So for the ACCC, the composite core is made from carbon fibers surrounded by a glass fiber matrix. And for the properties, the thermal expansion for ACCC is very low coefficient of thermal expansion, so it will reducing the sag at high temperature. Next, ACCR. The core is made by the aluminium oxide fibers embedded in an aluminium matrix, and the properties, ACCR have lower thermal expansion compared to the ACSR conductor. So this result in less sag for the ACCR. Next, we will move to the third HTLS conductor, that is ACSS. The core is made by steel similar to ACSR but with different properties. And the properties is the aluminium strand are fully annealed, providing greater flexibility and resistance to thermal aging. For the SSR, the steel core is made by the aluminium strand, and the properties for the SSR, it have higher thermal expansion, leads to more sag at high temperature, lower current capacity and higher weight. Next, we will move to the costing of the three type of HTLS conductor and ACSR conductor. For the ACCR, aluminium conductor composite, typically the range is $15 to $20 per meter. For the ACCC, the price can range from $3 to $4 per meter, and ACSS the price is from $2 to $3, and for the ACSR, $1.2 to $3.7 per meter according to the type used. So from this we can see that the ACSR has the lowest cost other than HTLS conductor, and ACCR is in the first ranking with $15 to $20 per meter, and followed by ACCC and ACSS, and the lowest cost is of course ACSR. So for the HTLS project, I have choose two. One example is from our country, and one example is at New England, United States. So for the example of project in Malaysia, TNB has incorporated HTLS conductor in various projects to improve energy efficiency and transmission line capacity. One significant project involved upgrading the 275 kilovolt transmission line from Port Klang to Kapar. This conductor is used to double the line capacity without the need for new right-of-way acquisition. And for the example of HTLS project in United States, the GSPL, that stands for the Granite State Power Link, is the project is made by the National Grid to enhance power flow from Canadian renewable energy source. The They use aluminium conductor composite core, that is ACCC, one of the type of HTLS conductor, to boost current carrying capacity with minimal sag. So it will improve the stability and efficiency in long distance power transmission. So this upgrade enable better performance with reduced line losses and lower resistance and integration of renewable energy.
Heat balance equation. First is about the thermal rating calculation. This equation balances the cooling and heating of the conductor to determine the current so it can safely carry. So the cooling must be equal to heating. So by rearranging the equation, we can find the implicit current I equal to square root QC plus QR minus QS over RT average. RT average come from AC resistance of conductor at average temperature. Alright, second equation is convective cooling QC. QC refers to the process by which heat is transferred from a surface to a fluid. This movement of fluid carries away the heat, effectively cooling the surface. QC depends on several factors, such as temperature difference between the surface and the fluid, the speed of the fluid movement, and the properties of the fluid. So to find QC, we need to calculate micro F absolute dynamic viscosity, PF density of air, KF thermal conductivity, NRE dimensionless Reynolds number, and T film. So by substituting the value of the parameters, we need to compare what who is the bigger between QC1 and QC2. So the bigger one will be the exact QC. Next are radiative cooling QR and solar heating QS. So what the difference between QR and QS? QR is a radiative cooling. Is the process by which an object loses heat by emitting infrared radiation. So all objects emit thermal radiation based on their temperature. This radiation carries energy away from the object, resulting in cooling. NQS is a solar heating, refers to the process by which an object absorbs energy from the sun's radiation, leading to an increase in its temperature. The form of heating is driven by the sun's electromagnetic radiation, primarily in the form of visible light and ultraviolet radiation. Now let's move on to the maximum ampacity calculation for SCSR trick. First and foremost, we need to find the micro F. So the micro F value is 1.9982 times 10 power of negative 5, PF 1.041, and KF 1.02871. Next, By indicating the wind speed is 1 meter per second, we need to find QC1 and QC2. So, based on the calculation, QC1 is selected because QC1 is bigger than QC2. Next, we find QR. So, by substituting the parameters value, we got 30.0205 and QS 14.07, and the amplicity current when wind speed equal to 1 meter per second is 10,286.7008 ampere. Alright, next, when wind speed equals to 2 meter per second, the amplicity current is 1544.7358 ampere. When V equal to 3 meter per second, 1731.0847 ampere. When wind speed equal to 4 meter per second, amplicity is equal to 1878.6324 ampere. And lastly, when wind speed equal to V meter per second, amplicity is equal to 2002.6387 ampere. So how about HTLS Dublin? So for HTLS Dublin, the micro F value is 2.1728 times 10 power of negative 5, PF 0.9292, KF 0.0317. So first and foremost, we calculated the QR and QS value. So the QR is 87.0067. QS is equal to 14.07. So when V equal to 1 meter per second, QC1 and QC2 is calculated by substituting the value parameters, and it shows that the QC1 is selected because QC1 is bigger than QC2. So we can directly calculate it for the amplicity by substituting the value. So we got the wind speed equal to 1 meter per second, the empty current equal to 2000.5488 ampere. By repeating the same steps, we calculate for the when wind speed equal to 2 meter per second, amplicity equal to 2340.0333 ampere. When wind speed equal to 3 meter per second, the amplicity equal to 2600.0289 ampere. When the wind speed equal to 4 meter per second, the amplicity equal to 2806.6784 ampere. And another one, the last one is when wind speed equal to 5 meter per second, the amplicity for HTLS Dublin is 2981.1259 ampere. Alright, after calculating the maximum ampacity for the SCSR and HTLS, we can collect the data and convert it to the graph to see how the changes of the ampacity current according to the different wind speed. Let's discuss together. From the calculation, we can determine both SCSR drag and HTLS Dublin show an increase in current ampacity with increasing wind speed. As wind speed rises, the conductors can carry more current without overheating. From the collection of the data, HTLS Dublin conductor exhibits a higher maximum ampacity compared to SCSR. So it shows the HTLS is more efficient at dissipating heat, allowing it to carry higher currents. And it's a better reliability and efficiency. From the graph, we can conclude that HTLS Dublin is a preferable choice for application requiring higher current capacities.
Now let's look at the effect of wind angle based on the calculation. When we talk about the wind angle, the value that's changed is the K angle, which in this case, the K angle is varied from 0.1, 0.5, and 1.0. When K angle is changed, the QC1 and QC2 is the only value that's changed. So for the ACSR tricks, when wind speed is equal to 3 ms, for the angle, K angle is 0.1, the QC2 is greater than QC1 as we can see in the slide. That makes we choose QC2 over QC1 in the calculation. So the ampacity that we got is 672.5942 ampere. So for the K angle 0.5, the QC2 is also greater than QC1. That means we choose QC2 over QC1 in the calculation. So the opacity that we got is 1258.2409 ampere. Lastly, for the K angle is equal to 1.0, the QC2 once again is greater than QC1. That makes we choose QC2 over QC1 in the calculation. So the ampacity that we got is 1731.0847 ampere. Now, let's see the calculation for the HTLS ACCCW when wind speed is constant at 3 ms. So for the K angle equal to 0.1, the QC2 is greater than QC1. That makes we choose QC2 over QC1 in the calculation. So the ampacity that we got is 1192.8146 ampere. So for the K angle 0.5, the QC2 is also greater than QC1. That makes we choose QC2 over QC1 in the calculation. So the ampacity that we got is 1947.3453 ampere. And lastly, for the K angle is equal to 1.0. The QC2 once again is greater than QC1. That makes we choose QC2 over QC1 in the calculation. So the ampacity that we got is 2600.0289. Now, here is the graph for effect of wind angle when K angle is varied from 0.1, 0.5, 1.0 at wind speed constant at 3 meter per second. By looking at the table, here is the result for the calculation earlier that we got from the K angle 0.1, 0.5 and 1.0. At the graph, we could see that the data from the table has been plotted, and we could see that the more perpendicular the wind angle to the conductor, the higher the ampacity, which means more power can be transmitted along the transmission line. As mentioned earlier, capacity value for both conductor increase when the wind angle is more parallel with the conductor, which means it has better power transmitting. This happens because the more parallel the wind angle to the conductor, it gives better and consistent airflow along the conductor. So it reduces the temperature of the conductor, that reduces the resistance and also reduces the amount of thermal sag. But overall, we could see that wind angle really does affect the performance of the transmission line, which means the more the more perpendicular the wind angle to the conductor, the better the performance of the transmission line. But from the overall performance, we could see that HTLS is better than ACSR in any wind angle. In conclusion, HTLS is better than ACSR by overall performance. It has many advantages and potential over ACSR. For the potential, HTLS is always preferable because it has better operating temperature that makes it last longer than ACSR. Also, by having higher ampacity than ACSR, may it transmit more power than ACSR. For the advantages, HTLS also has lower sag at high temperature that allows the transmission line to have longer spans. By operating temperature is high and be able to withstand the extreme temperature, makes it more reliable than ACSR. For the drawbacks, HTLS is not so popular because it is expensive rather than ACSR. Why? Because it needs a stronger structure since it's heavier and more complex installation that will cost higher than ACSR. And also, it is limited in the market